Peace out, fellow students. This is your favorite math prof, and today we're talking about derivatives. Derivatives are actually a very, very beautiful concept. You don't want to miss it, and if you understood the simplicity of it and the beauty of it, and it's almost always possible with every mathematical formula, you can form a derivative, and what the derivative allows you to do is to extract information about change from some graph and some function that you have. Okay, so let's say you're looking at an object that's moving in physics, for example, and you register basically over time the position x of the object, and this is then the axis of time. And now let's say 1 meter, 2 meter, 3 meter, 4 meter, and so forth. Right? You need 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, and so on. Right? So let's say this object that we're looking at starts at 0 and then moves after 1 second, it's 1 meter. A car, for example. After 2 seconds, it's already 4 meters. After 3 seconds, it's already 9 meters. And so on. Okay. So we can basically write a function here. Goes like this. Okay. So maybe I do a little bit. Maybe I do a little bit different curve. Let's have it a little bit more bent. Like this, okay? All right, so you now want to understand the average speed that an object has at a certain time, okay? So you want to know what's the average speed of the car at this position, or let's say in this time. So right, so we can basically say the average velocity is the amount of distance x an object takes in a certain time, right? Imagine you're running in the morning, right? So the average running speed, I'm sure you've calculated that, is basically the amount of miles that you have divided by the amount of time that you use for that, right? So let's say V average has a V and like a bar on top of it. That would be like delta x, that would be here, right? And then we have delta t here, we divide it by delta t, and voila, we have the average speed. So far, so good, but we also may want to know how far or how fast the car is, or we ourselves when we're running. How fast are we at that very moment? Did we start slow and become faster, or did we start fast and become slower? Was there some variability? We want to know that, right? We want to know, if we're running, we want to know, are we fast in the beginning and slow in the end? So maybe then we need to condition ourselves more that we don't slow down towards the end. Or was it the other way around? Well, that may be the optimum way for us to run. So it's very important to understand what the speed at any given moment is, not just over the entire distance of the run. Okay, so this is the average speed, right? And now that would be if we put a line here, that would represent a straight connection between this point of delta x here and this point of delta t, right? It's a straight line here, but the entire graph is bent here, right? So it would not be a good representation. Okay, so let's use a different color here. Green will do just fine. And let's say we are taking a smaller interval, where we measure the difference, right? Let's say we have delta t from here to here. And then this representation is almost exactly like the curve, right? The curve is a little bit bent here, and it's not quite as exact as it could be. So we can make that interval shorter and shorter and shorter, and then this line that we drew here will become more of a tangential line here. And if we want to know what the momentary speed is at this point of time, we will calculate the slope of this line, because the slope of this line is in the format of delta x by delta t, is the velocity again. And so the way we do this is by, imagine we start with a function x, and we'll basically have here the distance between this and this we can represent as a letter called h, and then we have basically, we add the letter of h to any value x, right? So now this distance becomes x plus h, okay? And then the function of this is, of course, f1 of x to f of x plus h, right? Instead of delta x, we replace it with f on x plus h minus f of x, okay? And then we divide this not by delta t but by just h, okay? And what we do then is we let this h become smaller and smaller and smaller until this h is so small that we're not looking for the average between 5 minutes and 10 minutes, but we're now looking at the average between 10 minutes and 10.01 minute, 10 minutes and 1 second, 10 minutes and then 1,000th of a second, 10 minutes and less and less and less additional seconds, right? So we're really looking for the difference between two very adjacent points. And we do that with the concept of limes, which is the Roman wall, right? So and mathematicians use that to say this is a bordering concept, right? So basically the limit is the limes is sort of like a border that we can make smaller and smaller and smaller and make all values smaller and smaller and smaller within that border. So h becomes smaller and smaller, h converges towards 0, right? That's what this says. And then we have this divided by h. So now let's say our function is, this function is probably represented by an equation, namely x squared, right? And so v would be the limit towards 0 of x plus h to square minus x squared divided by h. And I'm going to use this black pen to have it better recognizable, let's put it here, is, right? And then we have x squared plus 2hx plus h squared minus x squared divided by h. And that is, or limit of, so x squared minus x squared, that cancels each other out. And then we are left with 2hx plus h squared divided by h. And so this becomes 2x plus h. And when h becomes 0, we're left with 2x. And now 2x is our momentary speed at each position x, right? Or that was a bit confusing. I apologize here. What I called x here is actually t. And I should have called that not x, but f von x. Okay? So basically, or let's do it like this. So here we have x, and here we have x. There's always functions. You always have like one value or group of values that you call most often x. And then you have f von x, which is the function value that belongs to each of those x's, right? So apologies for the slight confusion here. I hope you could still follow. So this y coordinate is f out of x, and this x coordinate is x, right? So, and the function was x squared here, right? And then we form the derivative. That's basically what we do here, and get to 2x, right? So basically, the derivative tells us about any momentary change at any point of our function. And now we can basically set in any x we want, right? Let's say 2x, like at point, like at 10 seconds, right? The speed is, or the momentary change is 20, and momentary change of distance over time is velocity, right? So the momentary velocity here is 20 meters per second, all right? And that's how you form derivative. Think about going from an average, like a secant that cuts the graph at 2 points. Make the distance of the secant, make it smaller and smaller and smaller and smaller until the distance between two x points is basically infinitesimally small. And that's the x distance we have, and then the corresponding distance in the y direction, we divide that by this small x distance, we get our momentary speed. Basically, the blink of an eye. Okay, so that's it for today. I hope you had some fun, and see you next time.